So this video is to help you go over the golden ticket for your Unit 7 test, Unit 7 being Chapter 5. I know it's a little confusing. This first chart, if this is your f of x, fill in the antiderivative of f that way and the derivative of f that way. So I'm going to go through and do derivatives first. I just feel always more comfortable with derivatives, I guess, in terms of my trig functions. So the derivative of sine is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. Derivative of cotangent is negative cosecant squared of x. Derivative of secant is that secant of x times tangent of x. Remember, there's a multiplication in there, two separate functions being multiplied together. Derivative of cosecant is negative cosecant x times cotangent x, again, a multiplication. Derivative of natural log is 1 over x. The derivative of 1 over x, I would first rewrite that as x to the negative first, which means its derivative is negative x to the negative second, or you could write that as negative 1 over x squared. So now let's talk about antiderivatives. The antiderivative of sine is what would I have taken the derivative of that led me to sine, and that's going to be negative cosine of x plus c, could have had a constant there. The antiderivative of cosine is what would I have taken the derivative of that led me to cosine? Well, I would have taken the derivative of sine plus potentially a constant there. The antiderivative of tangent, remember if you want to prove this one, you can rewrite tangent like this and then do a u sum, but we end up with negative natural log of the absolute value of cosine plus c. There's also the version that has the secant in there, if you want that. Antiderivative of cotangent, we could think about cotangent as cosine over sine, do a u sub with the denominator. So we end up with the natural log of the absolute value of sine. Again, you could make that negative and have a cosecant in there. That's up to you. The antiderivative of secant, what would I have taken the derivative of that leads me to secant? This is where things start to get weird, and these are the ones that don't show up all that often on our tests and quizzes, and they rarely, if ever, show up on the AP test, right? But we talked about the fact that we wouldn't be proper calculus teachers if we didn't study all 6 trig functions. That would just be mean of us. We wouldn't have taught you properly. The antiderivative of cosecant, natural log of cosecant of x minus cotangent of x. And remember, again, there's a couple different versions of these. This is just one version. That's the one that I was taught that I go with. But there's some other ones where you introduce negative signs. The antiderivative of natural log. You guys actually don't know how to do that yet. That requires something called integration by parts. The antiderivative of 1 over x, well, that's the same thing as the antiderivative of that x to the negative first. And remember, this is the kryptonite of the power rule. The power rule has to relinquish all of its power, and instead of just increasing the exponent and dividing by the new exponent, this turns into the natural log of the absolute value of x plus c. And that absolute value is necessary because we need to make sure our domain into the log function is positive numbers. All right, so this chart is a little confusing because then it's like, wait, what am I supposed to do here? Kind of think about this like 2 separate charts, okay? What is the antiderivative of secant squared? The antiderivative of secant squared would be tangent of x plus c. It's what would you have taken the derivative of that leads you to secant squared. This one, I'm changing to say cosecant squared. It's okay if on yours you don't, but the antiderivative of cosecant squared would be negative cotangent of x plus c. Antiderivative of secant times tangent is secant of x plus c. Antiderivative of cosecant cotangent, this is why I changed this one up here because this was a double typo. It's going to end up being negative cosecant of x plus c. The antiderivative of 1 over u, remember that could be written as u to the negative first. Haven't done calculus yet, but then the power rule fails us, so this is kryptonite. We end up with the natural log of absolute value of u. The antiderivative of e to the u, because this expression in the exponent perfectly matches that variable of integration, we can just say that becomes e to the u plus c. All right, so there's your chart of a lot of facts going on. Question 2. Values of a strictly monotonic function h and its derivative h prime are shown. Well, the reason monotonic is important, this means that this was 1-to-1, which means that we know h inverse as a function exists, right? And it's a function that passes a vertical line test, etc., etc. Find h inverse prime of -1. Well, I know that h inverse prime of -1 is equal to 1 over h prime at some mystery output value. So immediately I can say h inverse has -1 comma mystery, which means that h has mystery comma -1. And again, we know that this -1 is on the inverse because -1 is going into the inverse, okay? Well, why is this helpful for us? Based on what we have, we can use this buddy to figure out this mystery value that I need. H is supposed to have an output of -1. Well, here's H with an output of -1 when the input was 0. So this becomes 0, 0, 0, and my buddy has served its purpose, okay? I erase it on the smartboard. You don't have to erase your work, obviously. In fact, you shouldn't erase your work on an AP test. From here, then, I can focus in on what does this thing tell me? Well, this thing tells me to take 1 over h prime at 0, which is 1/2, which means that my final answer is equal to 2. So h inverse prime of -1 is equal to 2. Next one, h inverse prime of 4. Let me erase all my colors on here. H inverse prime of 4 is going to be equal to 1 over h prime of some mystery. And again, the reason this works is because if you zoom in close enough on any function at a given point, at the point, it will look like a line. And we did all that work to discover that the inverse line has the reciprocal slope. It was 1 over m in that video. So from here, sorry, I digress. We know that h inverse has an input of 4 and an output that's a mystery, which means that h has an input that's a mystery and an output of 4. So I'm looking for this mystery value so that I can work on this fraction up over here. Well, h has an output of 4 when the input was 2. So 2, 2, 2, and my buddy point has served its purpose. Goodbye. Now I focus in on what I was actually trying to find, which is this expression right here, 1 over h prime of 2. 1 over h prime of 2, which is 1/6, which means that overall h inverse prime of 4 is equal to 6 because we have that reciprocal happening. Now, something to be careful of. I worked with a student on this a couple times. I've worked with a couple students on this, sorry, not the same student. This one has a table. Sometimes you're given functions. Sometimes you're given coordinate points. Maybe you'll be given a graph. The trick is understanding how do you read, I have an output on h and I need to find the input. Well, on the table, you just look for the input. On a graph, you would look for the x value that creates the y value that's given. On an equation, you would set h equal to that y value and then solve for x. So just keep in mind that these questions always follow the same structure. The idea is that the derivative of the inverse at x is equal to the reciprocal of the derivative of the original at y. And then there's just a lot of different ways that you can find each one of those things. All right, next thing, getting back into some times with James Corden. So find f prime for f equals this mess. We've got chain rules, product rules, quotient rules all in there. And it says, hint, try to avoid the product and quotient rules. Well, how can we avoid a giant mess? I'm going to call this y. I can avoid a giant mess by introducing logarithms. So this will be the natural log of y equals the natural log of this whole mess. What I want you to do is I want you to pause this video and I want you to expand this out where division becomes subtraction, multiplication becomes addition, and we rewrite things with exponents. So take a second for yourself, pause the video, and write this out using logarithmic properties. Okay, well, our purpose here was to get the arguments to be a little bit nicer so that we can take the derivative easier, right? Because the derivative of this guy, if you did 1 over the argument times the derivative of this argument, that's so much work. This part right here, I chose to just leave this as 7x squared. You could, if you wanted to, keep expanding out with properties of logs, but this being your argument is not terrible when you go to take the derivative. All right, so I'm going to take the derivative with respect to x. So the derivative of the natural log of an argument is 1 over the argument times the derivative of the argument. This one, 1/2 will just hang out as a constant, multiple. Derivative of the natural log of an argument is 1 over the argument times the derivative of the argument. 1 over the argument times the derivative of the argument minus 1 over the argument times the derivative of the argument. Okay, so we're getting there. I'm going to do a little bit of cleanup work. So this will be 1 over y dy dx equals, the 4 and the 2 will cancel, and I'm left with a 2x cubed in the numerator and x to the 4th plus 9 in the denominator. This one, sine over cosine is tangent, so this will just be minus tangent of x. This one, 14 and 7 will cancel to be a 2. X over x squared will leave an x in the denominator. From here then, last thing I need to do is multiply both sides by y. So dy dx equals, parentheses matter, right? We have to have our grouping symbols. We want to take this whole right side and we want to multiply that whole thing by y. Well, what was y equal to? Y was equal to that mess up there, which was the square root of x to the 4th plus 9 times cosine of x all over, forgot my denominator, 7x squared. Okay, so then in this step I just multiply both sides by y, and then I just replaced with what y was equal to. So is this still a lot of work? Sure, but you're doing more of the work up front in the logarithm part rather than the mess with the work with calculus. Okay, there will be a second video that will take us through the rest of this golden ticket. So go ahead and switch to the other video if you need help with the last couple.